Hello. In this video we're going to be looking at quantum tunneling. Here's the potential of the problem, and let's draw it. So it's very much like the potential step we considered in the previous two videos, except for rather than going off to infinity at positive x, it comes back down again to zero in potential. So the form of the solutions again depends on which region we're in. Let's call these regions 1, 2 and 3. And the solutions in 1, 2 and 3 will depend on whether the energy of the particle is greater than the barrier height or less than the barrier height, just like before. When it's greater, we'll have plane waves in all three regions. When it's less than the barrier height, we'll have plane waves in regions 1 and 3, but evanescent waves in region 2. So we can draw them something like this. I won't draw the plane waves because we know what those look like. In region for the energy less than the barrier height, we'll have a plane wave coming in, and then we'll have either exponentially growing or exponentially decreasing solutions in the barrier, and then a plane wave over here. And again, I'd like to reiterate that when I draw these pictures of the wave functions, of course they're on different axes, they don't have the same y-axis here. It's just a convenient schematic notation. The other thing that's a bit misleading about it is that, of course, these are the time-independent solutions, but I've just taken a snapshot at a particular time. As time evolves, the phase of these waves changes, so you can think of them moving along, and so at this point we'll be moving up and down. So the fact that I draw them matched here is really just a convention, and in fact you can't even draw them matched at the other end. Note that we're going to need both the exponentially increasing and decreasing evanescent solutions in this case in order to match the boundary conditions. Okay, so let's take a look at the form of the waves in each region. Let's clear the board. Good. In region 1 we have the following form. That is, just like with the potential step problem, we're going to send in a plane wave from the left. We'll set the amplitude to 1 by convention, and we'll get a reflected wave travelling back into the left direction, reflected back from the barrier. In region 3, that is on this side of the barrier, we'll have the following form. So a transmitted wave heading over to the right again, but this time note that k is the same k as appears in phi 1. This is because the potential is the same in both regions. The potential is set to 0 in both regions. So in particular, the energy eigenvalues in these regions are as follows. That is, the energy is h bar squared k squared over 2m for both regions 1 and 3. So it really is the same k. In region 2, it depends on whether the energy is greater than or less than V0. For the case that energy is greater than V0, we have plane waves, where k prime is different now, because it solves the energy eigenvalues of the time-independent Schrodinger equation are as follows. So because of this additional V0, k prime does not equal k. And when E is less than V0, we have evanescent waves of this form, and the energy eigenvalues look like this. That is, we have a minus sign in front of the h bar squared kappa squared over 2m. So and this then ensures that for real kappa, E minus V0 is negative, or V0 minus E is positive, which is true when the energy is less than V0. And up here we have real k prime, giving E minus V0 is positive. So notice that if we can solve the case so quantum tunneling occurs for when E is less than V0. We have to get through a classically forbidden region. When E is greater than V0, we're simply scattering over a potential barrier of finite width. It's a tiny bit easier to solve. They're pretty much the same in terms of difficulty. And note that we can solve the case of E is greater than V0 and then get the solutions for E is less than V0 for free by making the following observation. We can just substitute ik prime that changes into kappa, and that will switch the form of the solution from here to here, and it will also make this change here. So we can solve one of these problems and get the other solutions for free. So let's deal with the plane waves predominantly, because they're a tiny bit easier. So let's do our usual thing. We have to just match the wave functions at the boundaries using the boundary conditions. We now have 4 unknowns, r, t, a, and b. but we also have 4 matching conditions. So let's write those down. So first, let's just reproduce the picture a little bit smaller down here. So first we have that the wave function must be continuous in space. So at x equals 0, we have to match wave functions 1 and 2, and they must be equal to each other. Substituting this into our, the solutions, the forms of the wave functions, we find the following result. 1 plus r equals a plus b. Next, we have to make sure that the derivatives are continuous. Substituting in, we find this result. And we have the same 2 conditions to apply at x equals L. Continuous wave function, continuous derivative, and these give the following 2 conditions. Okay, so it's not particularly intuitive. We have 4 equations and 4 unknowns, and we can solve for them. We'll do so in the problem sets. I'll just take the solution here. In particular, we're interested in, say, the transmission amplitude t to get into this region. And in particular, we're really interested in the probability of transmission, which, remember, is given by the ratio of the probability current density in the transmitted region to the probability current density ingoing. And if we evaluate that for the case that E is greater than V0, so plane waves everywhere, we find the following result. So the probability of transmission, the ratio of the probability current density in region 3 to that ingoing. In this case, it is just modulus t squared. The velocities of the particles you can think of as the same in regions 1 and 3 because the potentials are the same. And we get this expression here. Now, probably the most interesting thing about it is that we have this sine squared k prime L term, meaning that whenever k prime L equals n pi for integer n, we have what's called resonant transmission, meaning when this is fulfilled, this is 0, this whole thing is 0, and we have probability of transmission equals 1. So we can tune E, V0 or L to get this condition to be fulfilled, and it's rather interesting. Perhaps the more philosophically profound case is when E is less than V0. So a similar looking expression to this, except for we now have a shine instead of a sine. So we lose our resonant transmission condition. Sorry, let me just make a note of that name. So with E greater than V0, we can have resonant transmission. When E is less than V0, we can't, but it's somewhat miraculous that we can even have transmission at all, given that we have to pass through a barrier, which is classically forbidden. So quantum objects can quantum mechanically tunnel through barriers through which they couldn't normally pass classically. So this is the basis of an experimental technique called scanning tunneling microscopy. You bring down a measurement tip close to a sample, and you can, by applying a bias voltage, you can tunnel electrons either from the tip into the sample or from the sample into the tip. And what tends to be done, there are different methods of operating this, but they tend to run it in the constant current mode, in which you vary the height of your tip in order to maintain the same current coming through as you move the tip along. So then you record the height of the tip at different places, and you can use this to map out the effective height of the surface down to the atomic scale. So let me get a picture up for you here. So here's a picture of an STM image, as it's called, where you're really seeing individual atoms. So it's an incredibly powerful technique. This also resolves a bit of a paradox we had in the previous 2 videos, where we looked at scattering from an infinitely long step. And we saw that there was no probability for transmission in the sense of a probability current getting through, but there was nevertheless an amplitude for transmission. And I said at the time that what happens is if you were to measure a particle there, you could find one there, but you'd be providing the energy using your measurement device. So now we see what happens. Really, you're changing the form of the solution. Originally, we had the step that went off to infinity. When you bring a measurement device in, you're actually changing the potential landscape. You're making it possible for the particle to exist inside the detector, and so you're bringing the step back down again. So you're really turning the infinite step problem into the finite length barrier problem, and that's how you're able to measure the particle in that region. So I'm going to show you So this seems like an incredibly quantum phenomenon, and it is really, but there is a precedent for it in terms of evanescent waves in light, and I'll show you that in a separate video. Thank you for your time.